Sometimes it can be useful to apply strategies when balancing equations. One strategy that is often overlooked is to recognize polyatomic ions found on both the reactant and product sides of an equation. Let us focus first on example A. When looking at example A, we notice that the atom aluminum and the atom calcium appear on both the reactant and the product sides of the equation. However, the polyatomic ion known as nitrate, NO3, is also found on both sides of the equation. Thinking about NO3 or nitrate as one large group of atoms to be balanced can sometimes make balancing somewhat easier. Therefore, the parts of this reaction to balance found on both reactant and product sides would include aluminum, calcium, and nitrate ion. Parentheses around a polyatomic ion such as nitrate, or any polyatomic ion, reveal how many of that polyatomic ion are present in the equation. The value written outside of the parentheses reveals how many of that ion are particularly present. In this case, on the reactant side, we can see that there are 3 nitrate ions present. Yet on the product side, there would be 2 nitrate ions present. Therefore, nitrate ion is not balanced in this equation. However, if you look at both the aluminum and the calcium, you can see, since there is no number attached to aluminum, there is just one atom of aluminum on the reactant side. This is also the case on the product side. The same holds true for the calcium on both the reactant and product sides of this reaction. Therefore, we must begin by balancing the nitrate or NO3 ion. Recall that balancing requires you to add coefficients or numbers written in front of any reactant or product. The coefficient becomes a multiplier for all of the atoms or ions written for that particular reactant or product. Since there are 3 nitrate ions on the reactant side and only 2 on the product side, we'll be thinking about what multiple the values 3 and 2 could first meet up at. Since 3 and 2 are both multiples of 6, and they would first meet up at this value, a target value of 6 nitrate ions for each side of the reaction may be ideal for balancing. In order to create 6 nitrates on the reactant side, we choose a coefficient of 2, which will multiply the 3 nitrate ions that are already present. This now creates 6 nitrate ions on the reactant side. Likewise, to get 6 nitrate ions on the product side, we would need a coefficient or multiplier value of 3. 3 multiplied by the 2 nitrate ions that are already present creates the 6th that we are after. We can now see that nitrate ions are balanced with 6 on both the reactant and the product sides. Recognize, however, that the 2 written in front of aluminum nitrate, or AlNO3, also doubles the amount of aluminum present on the reactant side. There are therefore now 2 aluminum atoms present on the reactant side, yet 1 aluminum atom present on the product side. Therefore, a coefficient of 2 in front of aluminum must be written. This creates the 2 aluminum atoms needed for the product side. Likewise, the 3 written in front of calcium nitrate creates 3 calcium atoms on the product side. Since there is only 1 calcium atom present on the reactant side, we must choose a coefficient to balance that. Therefore, a coefficient value of 3 creates the 3 calcium needed to balance the reactant side. I've erased the inventory values written below example A to reveal what the balanced equation actually looks like. What we see is that there is a ratio of 2 for 3 as reactants, creating 3 for 2 as products. This is now the balanced chemical equation, which is typically the simplest ratio of atoms or ions present in the reaction. Let us now look at example B. Again, think about the polyatomic ions that appear on both sides of the reaction. In this case, we have the polyatomic ion nitrate, or NO3, as well as the polyatomic ion carbonate, represented by the symbols CO3. Recall that when a polyatomic ion is not written in parentheses, such as CO3 and NO3 in the circled cases, it represents there is only one of that ion present in that particular formula. That's an important detail to try to recall when balancing chemical equations. You must also recognize that the element iron and the element sodium are present on each side of the equation. One could take an inventory before beginning to balance the equation, although it's not always necessary. Let us inventory what's going on here. On the reactant side, we see that there are two NO3 ions. However, on the product side, since NO3 is not in parentheses, it reveals there is only one of them present. When looking at the carbonate ion, or CO3, we can recognize that there is only one of them on each side of the equation. Therefore, carbonate is balanced. Looking at the sodium, on the reactant side of the equation, there are two sodium present. However, on the product side of the equation, there is only one sodium present. Looking at iron, we can see that there is one iron present on the reactant side and one iron present on the product side. Therefore, iron begins balanced. Let us now choose a coefficient to begin balancing. Since we know there are two sodium, or Na, on the left side, we know that there will need to be two sodium on the right side, called the products. Therefore, a coefficient of 2 is a good choice to begin. This 2 doubles the amount of sodium present on the product side, creating what we would need, 2 sodium atoms on the product side. Sodium is now balanced. What this also does is doubles the amount of NO3 that was present. There was one NO3 to begin with, but by adding the coefficient of 2, it just doubled that amount to make it 2 NO3 on the product side. Therefore, NO3 is now balanced on both the reactant and product sides of the equation. When looking at all the other parts, the carbonate, CO3, it is also already balanced with 1 on each side of the equation. When looking at the iron, it is also balanced with only 1 on each side of the equation. Therefore, we now have a balanced equation by adding just the 2 coefficient necessary to create the balance of atoms or ions to arrive at the balanced equation. Let us clear our inventory information to reveal the coefficients necessary to balance this particular reaction. Coefficients of 1 and 1 on the reactant sides are needed, and 1 and 2 on the product sides are needed. Recall that when no coefficient is written in front of a reactant or product, the value is assumed to be 1. Since we wrote a 2 in front of the NaNO3 product, the coefficient represents 2. Let us try to balance example C without writing the inventory. For some students, the inventory crowds the information and sometimes creates more confusion than may actually be needed. Before beginning letter C, I've recognized an incorrect formula for one of the reactants. The reactant aluminum nitrate should not have a formula of Al2. It should have simply Al. Therefore, we will just cross off the 2. Without having the correct formulas written, balancing an equation is sometimes not possible. You can assume for the examples you'll be asked to balance that the formulas will already be written in correct form. Furthermore, we can see that sodium appears on the right side of the reaction, but not on the left side. This is not possible for chemical reactions since a simple rearrangement of atoms or ions is what occurs. Therefore, a second typographical error needs to be corrected before we can begin. The sodium will simply be changed to the potassium needed to balance this reaction, represented by capital K. Now we can begin to balance. In this particular reaction, recognize there are two polyatomic ions. One ion known as sulfate, or SO4, found on each side. One ion known as nitrate, or NO3, found on each side. Recall that when the polyatomic ion is in parentheses, the number outside the parentheses reveals how many there are. Therefore, on the product side for sulfate, SO4, there are 3 of that ion present. Yet on the reactant side, there is only 1 of those present, since there are no parentheses around SO4. This reveals a great place to start. Choosing the coefficient of 3 will triple the amount of SO4 present, changing it from 1 SO4 on the reactant side to 3. Therefore, this matches the 3 SO4 on the product side needed to balance. Notice, however, that there were already 2 potassium, or K, present. But when the 3 was placed in front as a coefficient, this multiplies that amount by 3, creating 6 potassium on the reactant side. With only 1 potassium present on the product side, we can see that a coefficient of 6 will now be necessary to balance the potassium on the product side. What this does is this creates 6K, or potassium, on the product side, which we already have on the reactant side when we look at the 3 written in front of K, which multiplies by the 2 that is already attached to potassium, or K. Now we can begin to check some of the other parts. We can see that aluminum found on the product side shows 2 aluminum, yet on the reactant side only shows 1. Therefore, a coefficient, or multiplier value of 2 should be written in front of the aluminum on the reactant side to double that amount. What this does is this creates the 2 aluminum needed to balance against the 2 aluminum on the product side. The reaction is now balanced for aluminum. This 2 also doubles the 3 nitrate, or NO3 ions that were already present, creating 6. The coefficient of 6 written in front of KNO3 on the product side created 3 NO3s, or nitrates, needed. Therefore, on each side of the reaction, there are 6 nitrate. We finished balancing with coefficients of 3 and 2 on the reactant side, and 1 and 6 on the product side.